I also want to thank ISES President Dave Renee, who is also instrumental in the organization of this event today. The webinar will last 1.5 hours and will include a question and answer section after the speaker presentations. My name is Jennifer McIntosh. I'm the Executive Secretary here at ISES headquarters in Freiburg, Germany, and I'll give you just a short introduction to ISES and the work we do, as we have many new participants joining us in this webinar today. ISES is a nonprofit membership organization. We are a UN-accredited NGO, and our mission is 100% renewable energy for all used efficiently and wisely. We represent a diverse membership of many different people working in all areas of renewable energy. And we work together with other like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ISES, which you can find more about on our webpage. Some of the benefits include exclusive access to presentation and webinar recordings, such as today's event, exclusive and unlimited, I should say. Members can also get discounts and even free registration to ISES events and our partner events. We also publish a newsletter for members where you can follow our progress and share your own news. And of course, members can also subscribe to our academic journal, Solar Energy, our flagship publication. And we just want to thank all of our members who are joining us today. And for those who aren't already a member, we look forward to you joining. So now just some brief information on the Q&A section before we get started with the presentations. For the Q&A section, we invite you to send in your questions, and we're looking forward to your participation. When sending in the question, please remember to write in who the question is for, and keep your question short and precise. Please feel free to start sending in your questions anytime throughout the webinar. Secondly, we're recording this webinar today. So the recording and the speaker presentations will be publicly available for only a few days on our website. And as I mentioned before, exclusive and unlimited access to these past webinar recordings and presentation is available in the members area. So I'm now happy to hand over to our moderator, Tom Stoffel. Tom is an atmospheric scientist with over 40 years of research experience in solar and atmospheric radiation measurements, including the design, development, and operation of the Solar Radiation Research Laboratory at the National Renewable Energy Laboratory in Golden, Colorado. Tom will introduce our speakers, and he will be moderating the question and answer session. Tom, thank you very much for joining us today. The floor is yours.
Thank you, Jenny, and welcome to 207 people that have signed on for this ISES webinar on measuring albedo. Today, we're very fortunate to have a distinguished panel of experts who will be sharing their knowledge to help us understand what is albedo, why this solar resource component is important to photovoltaics, how to measure albedo from ground-based radiometers, and how it is estimated from satellite observations and tower measurements. Please use the question portion of this GoToMeeting session to enter your questions, as Jenny described earlier. I'll be monitoring that and doing my best to address as many as I can in the time remaining following the last presentation. After the webinar, you can also send them by email to ISES or contact the presenter if you have that information. Now I'll introduce the presenters by supplementing what you see here on the slide before us. Richard is the Chief Technical Officer at Suntrace and brings his vast knowledge of solar resources and performance modeling of PV and CSP systems. Ravi brings decades of experience developing renewable energy power systems in India, Central and South Asia, and we thank him for serving on the ISES Board of Directors. Kees has more than 20 years of experience with radiometer design, as evident from the Hukseflux product line, and his involvements with the International Solar and Atmospheric Radiation Measurement community. Jan Peter has decades of experience in atmospheric physics, supporting a wide range of global and interplanetary scale research interests based on satellite remote sensing, including surface albedo. Before we begin, I want to remind the presenters to watch that chat window for my timing cues. With that, Richard will now give us a common basis for discussing albedo and why it's important for solar energy conversion. Richard, please take it away.
So hello everybody, this is Richard Meyer from Suntrace. Thank you, Tom, for moderating this, and I'm very happy that now this webinar can take place. I could motivate Dave Rene to take up this idea, and I'm very happy to have a very renowned
Hello, Richard. We seem to have lost your voice. Jenny, can you
Richard?
hear me?
Yeah, now we can hear you again.
Yes.
Can you go back about 20 seconds?
Okay. This is the title slide. You can see that?
Yes. Yes, we can see.
Okay, good. So, yeah. So my goal is, as said, to give an introduction into the topic of albedo with the main aspect of how does it affect the solar yield of PV plants, and what are some practical things to consider when measuring or deriving it.
Richard, we seem to have lost you again.
And I remember its meaning whiteness. So it's about the reflection of Earth surface, but also you can think of the reflection from the cloud, so that we can differentiate between the ground albedo and the albedo seen from the sky. We will hear more on that, I guess, from Jan-Peter Müller on the satellite section.
Richard, we lost audio again. Richard?
As the global horizontal irradiance. So this is a relatively simple view. We assume the light is reflected in all directions in the same way. So we have isotropic reflection. If you take a
Richard?
Hello, Richard. We've lost audio.
Richard, we can't seem to hear you. Could you start over again?
So I have unmuted.
Yeah.
You can hear me?
Yes. You keep...
From which you could not hear anything?
It'd probably be best if you start over.
From the start?
Yeah.
So here we go.
At least for this slide. At least for this slide. What is the meaning of albedo?
Okay, okay. So there was some interruption. Sorry, I can hear you very well. So the meaning of albedo, briefly explained. Basically, it's about how much light comes back from the ground, or if you take a view from the satellite, how much is reflected back.
Hello, Richard. Something's wrong. Richard, audio?
Can you hear me?
You keep dropping out, Richard. May I suggest that you call in by phone?
Or did you just change your speaker? If you just change your speaker, that sounds better. You're sounding better now.
My speaker, I mean, I can hold my microphone right in. Okay, it's indicating it's working quite well. I can use the built-in microphone. I switch. So this is now the built-in microphone. Can you please verify you can hear me?
Very good.
Hello?
Yes,
Hello?
we can hear you. Richard, we can hear you now.
Okay, great. Okay, so I may continue. And just a very brief repetition, we differentiate in the what we call the simple albedo, and you can take a closer view into bidirectional reflectance functions. I don't zoom into that, but hope that Jan-Peter Müller is explaining more about that. Let's continue. So first, how to measure albedo, and I'm pretty sure that Kees from Hukseflux, he will explain much more how these instruments actually work. So basically, you have two sort of instruments. One is looking upward into the sky, and the other one is turned around and measuring the upwelling reflected. So what you see on the right side is a classical pyranometer. Similar you could do and might be quite useful if you simply use like photodiode sensors. On the right-hand side, you see such a setup. So question is how this backscattered sun radiation is having influence on PV yields. So we have basically what we usually call the global tilted irradiance, or some also plane of array irradiance. So there actually the diffuse plays a major role. So you can imagine that the diffuse radiation is also accepted by the PV panel, and for that reason you might see some increased yield. This slide shows you how that actually happens. So if we vary the surface tilt from 0 to 90 degrees, we can see that the diffuse irradiance, depending on, you see here various albedo values, how this is increasing. And down there, the lower graph shows you that there might be an optimum in this case, like around 35 degrees, you get the maximum effect, and you certainly recognize that the higher albedo helps to get more GTI. So some basic considerations. What are typical values of albedo? What are we talking about? There is like dark forests, which have just a typical albedo in the range of 5 to 15%. Grassland might be, depending on the soil moisture and so on, between 10 and 25% if it's really dry. Sand, there might be dark sands, just 15%. There might be bright sands, white sands, up to 40%. Snow, of course, is the most bright we can imagine on surface, between 15 and 40%. And a water surface, although we frequently see the sunlight and think water is really reflecting strongly, this is just under certain angles. So here really bidirectional reflectance plays a major role. But if you look into clean water, into the ocean, you might experience only 5% albedo. Surface can change significantly across the season. This depends, of course, on the vegetation mainly. So this gives you some examples, and I guess we might see more on that from especially the satellite images. So we're typically in a range between 0.2, like 20%, and might see some increases if you see vegetation flowering or dry and so on. So this is some examples for such seasonal cycles. Getting to practical issues of ground measured albedo. So this is zooming into a potential PV site. We measure typically only at one position in the usual case. So we might have, depending on the height of the instrument, the albedo meter, we might see different angles. It depends on where we measure. If you're measuring in the darker surfaces, you might see substantially lower or brighter parts. So albedo is quite variable, even in the small scale. So this is just a simple assumption. This graph shows you how many square meters are covered if I increase the albedo meter from 0 to like up to a tower on 100 meters. So, but certainly for practical reasons, it's quite difficult to install such at installation heights of 10 meters. Even then, 10 meters is a typical wind measurement at the PV site. But even then, we will have problems in installing regular cleaning. So consider these practical aspects. Then I already told surface can be quite heterogeneous within one PV lot, which is usually covering several square meters, square kilometers. There might be, for the measurement itself, disturbing objects really close to. So usually such a met station is housed, it's in a fence, so the fence might influence. And most importantly, usually we start measurement of albedo at a certain point in time, but to observe the cycle, we would like to have also measurements back into time, ideally over several years. Then we might even observe some changes in ground albedo. Just a few examples on regions where we are facing quite strong albedo, like in Chile's Atacama Desert. There is a Salar de Atacama, which is a salt lake. There's another one in northern Namibia. So in such regions, you might experience really strong albedo as well. So how does this at the end affect PV yield? First example is on conventional PV. So what we see here is a thin film, which is with increasing albedo from very low values to very high. We see some dynamics, but it's actually zoomed in, so it's not as strong as you might think. Bifacial modules, this is what Ravi will talk more about, will take more advantage of also harvesting the illumination on the backside. How can we simulate such in principle? There are several software tools out there. We did our simulations here using PVSys, but just last week we noticed that SAM also was updated and now can simulate bifacial modules. Similar PVSol and PVLib, so this is more and more increasing. What I want to say, kind of a shortcoming, is all just consider isotropic albedo, none of them VDRF. So just a few examples on how does this affect the annual energy production of various PV technologies. So here, what you see here in this example is for a 50 megawatt plant, what is the plant in Tunisia, where we might see in the desert lands quite strong albedo, getting all the way from 0 to 100. We experience on the low side, you see what I've shown you before. This is the conventional polycrystalline silicon, and putting the same or a similar technology, but bifacial, having also a chance of receiving photons from the backside, you get a very strong increase in the yield, increasing albedo. So this is the main reason why we're mainly sitting here together. And just a few more words on that. So this is giving you some examples how this, in this case, is increasing for each % of albedo, how this is increasing the yield. Bifacial modules are quite sensitive to the tilt angle. This is what you see here. They're also sensitive, as you can imagine, to the distance between the PV modules. So, of course, the greater the distance, the more sunshine is down on the ground, reflected from there, and you have an improved yield. Of course, this is also requiring larger land size, longer cables, and so on. So what we do when we do an optimization, we consider monofacial or bifacial in some cases, and when optimizing search, you have to consider not just the tilt angles, but of course also the row distance. In general, one observation is that these bifacial layouts show an optimum and slightly higher tilt than the monofacial. To close, I just want to give you one example for a plant which we supported, which is in Namibia. So this is not too far from the Salt Lake. You've seen on the big map. And if you zoom into and just take a look in the surrounding of the plant, we notice that from the satellite-derived albedo, from the MODIS satellite, we have noticed that in the closest surrounding of this plant, we noticed that albedo was in the range from like 11 to 22%. So there is really quite some difference, and it is an additional aspect, especially if you are thinking about mounting bifacial modules, to really think, to analyze, to assess, and measure the albedo. Just to give a few numbers, price-wise, so we could imagine getting back to the Tunisia plant. If we put the same plant, the place where we have like 10% higher albedo, we end up with some additional yield in the order of 3%, assuming like a typical price of $55 per megawatt hour, like 5.5 cents. This each year would lead to an additional of about $160,000. So to summarize this, the main aspects I see which should be considered for albedo and PV, first of all, you should think about what is the soil type, what is the vegetation, because there is quite some variability, and it can lead you to substantial additional earnings. You should also consider that ground albedo varies temporarily. So we have the change in soil moisture, we have vegetation, but what also should be considered, we might analyze during the site qualification the albedo, but it might change dramatically when you actually erect the PV plant, because you do, in many cases, changes to the soil. In general, albedo is tricky to measure on the ground, but also not so easy to derive from satellite. What we observe also is what's pretty clear. In general, high albedo is favorable for PV. It's almost negligible for conventional PV, but has a very strong effect for the bifacial modules. I didn't talk about Suntrace. We actually measure albedo with our helioscale stations. We do solar resource assessments where we apply this measured plus the satellite-derived albedo. And we also consider such in PV yield assessments and techno-economic optimization. So I want to thank you. If you have questions, I think they will be put at the end. But I'm also open for reaching, for emails and so on. Thank you.
Thank you, Richard. Thank you for that. That really gives us a good, strong basis for the rest of the presentations here. Next, and then I have recorded questions here to the audience. We are now at 237 attendees, and I've got quite a few questions. So, Richard, we'll get back to you on those. Next, we'll hear from Ravi about additional yields using bifacial modules and the dependency in albedo. Ravi?
Hi, Tom. Good evening and good morning to all of you. And thank you, Tom, for monitoring the session, and thank you, Jenny, for this opportunity to speak this evening from India. And I welcome all the participants who are participating today evening. And I'll be speaking on the additional energy. Additional energy of yield from the bifacial modules and the dependency on albedo.
Robbie, can you just use your keyboard arrows to advance the slides, or click on the arrow on the slide?
Yeah.
There you go. Okay.
Right. I was not getting my keyboard. And is that yeah, right. Now I can say. Can you see my screen?
Yep, we can see your presentation.
Okay, fine. Thank you. And if you see, the first slide speaks about the difference between the monofacial and the bifacial modules. If you see the monofacial module, you have the front glass, then the cells, and the back sheet. And for the bifacial module, you have both front side and back side. You have back side as a transparent, which could be a glass or it could be a transparent back sheet. And you can see the contacts on both the sides. And if you see the first example, that if you see in a monofacial cell, you have only the front power, which in this case, I've been given an example, which gives you 345 watts. And ISC is something like 9.1 amps. And if you see the same module, cells used in a bifacial cell with 15% reflectability, ground reflectability, you can getting 388 watts. You have a straight 15% increase in the short circuit current, which comes 10.46 and so on up to 30%. And let's understand what contributes to the energy yield. And bifacial energy gain depends on the type of cell used for the module and also the bifaciality factor. The definition for bifaciality factor is the ratio between the power of rear side module at standard test conditions upon power of the front side module. The first point of the energy gain is the bifaciality factor of different bifacial solar modules. For the cell type port loss is greater than 70%. For the port type cells is greater than 90%. For HIT type of cells, 95%. And for IBC is 70%. If bifaciality factor is more, the energy yield will be more. The second point for the energy gain is the location at site. Content of diffuse radiation and direct radiation affect the energy yield, and also the latitude decides the tilt angle of the mounting system. If diffuse radiation continues, it will lead to more generations. The third point which contributes is the tilt angle. The tilt angle increase will cause increased reflected light and hence contributes to the energy yield. The fourth point, the contribution of albedo to the energy yield, is the type of horizontal surface from which, and the reflectivity, the albedo factor just Richard mentioned. If you see some of the factors, if you see have a greenfield grass, which is contributes something like 23%, concrete is 16%. If you have a white painted concrete surface, 60 to 80%. You have white gravel, it's something around 27%. And white roofing material will contribute to 56%. And the light gray roofing membrane contributes something like 62% reflection. And the roofing membrane white will give you something like 80%. The fifth point, what Richard also mentioned, I'm reiterating again, is the row to row distance. If you now space the modules in increased distance, they'll contribute to the yielding factor also. Then the sixth point, if you see the presentation, the elevation and height of the structure. If you are using a flush mounting blocks, the light on the rear side is blocked, and less height will cause self-shading on the rear side of the module. And as you see from the graph, for a 30-degree tilt with 2.5 meters of inter-row spacing and with 80% albedo factor, the optimum height will be attained around 1 meter. installation height. This is some story done by some of the industry stalwarts. And also, there is contribution if you're using a single axis tracker, and that enhances the energy gain and will boost the energy up to certain levels. And a study by Enarial says that if you see the picture around the vertical installations, due to direct sunlight to front side and the reflected sunlight to the rear side, the yields are very higher. So you can look at for some of the installations like facets, which could contribute to the energy for the bifacial cells. And this I'm presenting a study by San Diego National Laboratory in the USA. How about the bifacial gain, this how they vary throughout the day. And the bifacial contribution is more during cloudy conditions. And it shows that bifacial modules outperform from various factors as compared to monofacial modules. And the picture shows about the 15-degree tilt, about 30-degree tilt, 90-degree tilt, and different facing. And you can see the study showing the effect on the bifacial module. And the study by Trina Solar himself said that they tested in Changzhou in the factory that how much more energy bifacial modules can give as compared to monofacial modules. And you can see the bifacial gain on grass is something like 5.2%, but the best is obtained on a white painted surface with a tracker, which is close to 33%. And study by Solar World defines the bifacial gain energy that increases with the tilt angle, the height of the ground, and the albedo of the ground. With the equation, bifacial gain in energy in percentage, A times theta plus B times H and plus C times alpha, which are where A, B, C are numerical coefficients. High albedo gives higher energy yield, higher the installation height of the module, higher the gain. Bifacial boost is greater on days with lower insulations. And bifacial modules provide a considerable performance in more than ideal circumstances. And if you are looking at investment and looking at LCOE and the prediction by Lungi Solar with different kind of insolation level varying from 1,000 kilowatt per kilowatt peak to 2,000 kilowatt per kilowatt peak, and with different kind of cost levels, and you see that the cost will very soon drop below 5 cents per kilowatt hour for most of the regions in the world. And this is very effective for higher sunshine regions where it will pay off sooner or later. Finally, in my conclusions, I can say that the bifacial solar modules gain in energy will depend on module bifacial factor, albedo, and the tilt angle. And bifacial module performance is very sensitive to enhance albedo on the ground surface. You just heard from Richard about the different techniques of albedo measurements, and one should use these techniques to ensure effectiveness of bifacial modules. And also from the study of San Diego National Laboratories, we have seen that east and west bifacial vertical modules, they can outperform optimally oriented as compared to monofacial modules with enhanced albedo. Also, vertical east-west bifacial modules produce energy only in the morning time or evening time of the day. Bifacial modules also will significantly outperform monofacial modules in conventionally designed systems and will benefit from bifacial modules with optimized design, and also preventing the minimized ground sending beneath the array and the backside obstructions. One has to be careful about the installations of bifacial modules. Careful design and parameters choice for both modules and installations will definitely ensure better performance of bifacial modules. And with the various studies done, as you may recall, that currently bifacial module constitute less than 5% of the total production. However, the various studies point towards achieving levelized cost of electricity below 5 cents per unit in the days to come. Thank you.
Thank you, Ravi. We've got some questions coming in for Ravi as well. We'll hold those till the end. Right now, I'd like to introduce Kees, who will now share his expertise in radiometry for measuring albedo. Thank you.
Hello, everybody. Here's the Netherlands, Kees Van Den Bos, how to measure solar albedo. I want to treat several subjects. First of all, PV system performance monitoring, then go into the performance model, discuss a little bit about standards and instruments, and finally, recommendation. My company, Hukseflux Thermal Sensors, is a leading manufacturer of pyrometers and albedo meters. And additional input for this lecture came from Groundwork Renewables from the United States, which is a leader in providing meteorological and soiling data to the PV industry and very experienced in albedo. Both companies are dedicated to bringing measurement to the next level. So we are basically measurement fanatics. About the terminology, you are all familiar with global horizontal, with plane of array. I also will use the term reflected horizontal and reflected plane of array. Albedo is typically understood for horizontal mounted instruments. If I talk about the resource assessment, I talk about pre-construction, so before you construct a PV power plant. And when you use the term performance monitoring, I typically talk about operational, so when a power plant is operating. So here you see an example of a pre-construction albedo measurement when the field is still bare. And here is an example of operational PV monitoring when the power plant is running. On the left-hand side, you see a pyrometer facing up. On the lower right-hand, you will see a pyrometer facing down, basically measuring albedo. I wish to stress that this is work in progress. So the PV industry is learning how to perform measurements, how to use albedo data as input to the performance model, and how to perform uncertainty evaluation. The big challenges here are that albedo is spatial variation, albedo has seasonal variability. And well, to put it short, it's difficult to find one representative location for reflected horizontal or reflected plane of array irradiance. Life is very difficult with albedos. Let's take you back to the times when things were still simple. Conventional non-bifacial PV power plants, you just have two pyrometers, one facing horizontal, one in plane of array. People measuring solar radiation, they nowadays more and more work with the ISES standards. Actually, there's a group of 3 standards. The group is called 61724. And number 1 is about monitoring. Number 2 is how you evaluate the system capacity, basically using 2 sunny days to measure the PV performance of a power plant. And number 3 is about system energy evaluation, basically monitoring for 1 year. This IEC group of standards is gaining importance. The IEC also defines what is a performance model, and this concept is important. The performance model is a mathematical description of the electrical output of the PV system as a function of meteorological conditions, system components, and the system design. This model is agreed upon in advance by the stakeholders of the test. So basically, performance model, remember that term. IEC defines as purposes of monitoring localization of faults, identification of performance trends, and comparison of performance to design expectations and guarantees. The last 2 obviously compare to a certain baseline, which is your performance model. end result of PV monitoring often is a performance ratio or performance index with a certain uncertainty. That's what the banks basically ask for. And if you start measuring albedo, your first step is to ask yourself, what does the performance model require as input? Maybe it's albedo, maybe it's not. And secondly, what do you do for specific purposes? Maybe reducing uncertainty, and it could be employ multiple instruments or construct a tower. IEC works in different classes. Basically, these are accuracy classes, class A, B, and C. So there's 3 classes, A, B, and C. For big power plants, you work with the highest class, A. IEC defines requirements with each class for instrument type, for cleaning intervals, or for calibration intervals of instruments. This is a typical class A instrument. It's a meteorological system. Of course, also electrical power is monitored, but the requirements for a class A system are a ventilated and heated pyronometer, one on plane of array, the other global horizontal irradiance, then wind, panel temperature, air temperature, but not only that, also calibration interval and cleaning intervals are required. What you expect when you expect albedo? Well, on class A systems and not on class B and C, for example. How do we measure albedo? Well, basically, this is a pyronometer. It has 2 glass domes. Solar radiation comes in through the glass domes and hits black detector. Below the detector there, or the detector is a thermal sensor, and it gives off a signal proportional to the solar radiation. A pyronometer comes with calibration and test reports, and this particular one also includes heating and the tilt sensor. A pyronometer is nowadays the de facto standard in PV monitoring. It measures solar irradiance and in watts per square meter, and it defines the maximum yield independent of what panel type you actually use. It has a characterized directional and a characterized temperature response. Pyronometers are spectrally flat, which means it catches all the radiation and gives it the same weight. It's suitable for all orientations of instruments and can serve as a reference for all PV cell types. It's not the only option that you have. You can also use reference cells, which is basically a miniature PV panel, and the reference cell measures solar irradiance as used for power generation by the particular PV panel. You have to be careful. A reference cell must match the PV panel of the power plant, so it must have the same cell type and also the same type of anti-reflection coating. PV reference cells are not suitable for horizontal installation. Pyronometers versus reference cells, you can talk a lot about it. The IEC standard that I just mentioned allows both. The International Energy Agency recommends use of pyranometers only. Going on about pyranometers, pyranometers come in different accuracy classes. This is the ISO standard 9060 that covers pyronometer accuracy. There's 3 classes again, A, B, and C, high accuracy, lower, and the lowest. In IEC monitoring class A, you expect high accuracy, so class A pyronometers. In class B monitoring system, you expect lower class instrument. In class A, going on about that, you also require heating, ventilation, calibration, and cleaning. Why heated pyronometers? Basically, you avoid all kinds of measurement problems with dew and frost. So this is a heated pyronometer, this one is not heated. The IEC standard, of course, starts with the most important measurement with plane of array. So with one-sided conventional PV panels, usually albedo is just not measured at all, but with bifacial PV this changes. And then somewhere in this IEC standard, in clause 5, you will find that it recommends plane of array, a measurement, to go together with local albedo measurement to demonstrate consistency what is assumed in the model, that is the performance model, and also to include in the documentation of your uncertainty. So what does an albedo meter look like? It looks like this: two instruments back to back. You can also make them modular so that you can take them apart. You can also use separate instruments. So here's the global, reflected, and plane of array on one boom. Why do you need modular instruments? Well, you need to calibrate them, and then it's easy to take them apart because you can use them in the standard indoor calibrations facility. So here you see a pyranometer being compared to a reference pyranometer in an indoor facility. So going back to the resource assessment, here you see a typical pre-construction resource assessment. What do you do there? Well, you make installation of about 1.5 to 2 meter height. You take an unobstructed site, and what you should really be careful about, and that's what Groundworks tells me, define your land management strategy. So if you expect vegetation there, use a vegetated area. If you want to keep the soil below your panels bare, use a bare assessment. From pre-construction to operational. So we already saw this Class A system, and here you see a plane of array on a moving tracker. So that's an example of a Class A system. Here you see again the photo of the two pyranometers. So you can also include albedo measurement, and the one at the bottom is obviously installed in between the rows and facing the green vegetation, but also the shadow of the PV panels. Here is an example of an unobstructed station, used also sometimes for operational structures to serve as a reference. So an unobstructed albedo measurement can also be used for albedo. It can used as a reference for satellite measurements. We will hear more about that later. And it can also serve as a reference for multiple instruments that are installed at the PV array. So here's a picture of what might happen with bifacial modules, and here we only had limited installation choice. So here you see one instrument facing up, but if you take a close look in the same instrument, there's also one instrument facing down. So this is basically the same picture. What are people using for instruments? The most common instruments are spectrally flat pyranometers. So you use the same for global, for reflected, and for plane of array. Why do people do that? Well, one reason is that the PV system model expects spectrally flat horizontal radiation as input. That might not always be true, but for most people that's the state of the art. I expect that to change, and what the model then does is use an empirical calculation in its performance model to calculate back reflected plane of array irradiance. You have alternatives. You can also use multiple lower cost instruments, for example, spectrally flat Class B. You can also use PV reference cells for plane of array reflected irradiance. My last slides on recommendations. So if you start measuring albedo, first look at the requirements of your performance model. Secondly, focus on reducing spatial uncertainty by taking multiple reflected horizontal irradiance measurements. So the recommendation of the ISC is 1 for every plane of array. Another recommendation is to deploy at least one obstructed albedo measurement. You could see how difficult it is to measure between rows, so to have some kind of unobstructed reference is really very nice. Last but not least, keep logistics simple. It's not easy if you use many different instruments, so there is something to be said to use the same instruments for all measurements. And usually, right now, these are spectrally flat Class A instruments. Last recommendation, use separate pyranometers or modular albedo meters consisting of 2 pyranometers because that's easier for recalibration. We have a question and answer session, but your contact at Hukseflux is me. If you want to know more about stations, please contact Justin Robinson of Groundworks. Thank you so much so far.
Thank you very much, Kees. That was really great. Let's see, moving right along. We are getting questions. We have over 200 folks in attendance here, so they're coming in. I'll do my best at the end of Peter's presentation, which we'll hear from about deriving albedo from satellite-based observations and tower measurements. Peter, you ready?
Yes, good afternoon, good evening, and good night, so to say. So I'm going to talk about global and local surface albedo measurements. Obviously working in the university, I'm going to highlight the output from several different research projects in which we're looking at many different aspects. But fundamental to all of this is the actual definition itself, which was previously mentioned, and the bidirectional reflectance distribution function, which was defined initially at someone at the US National Institute of Standards and Technologies in Gettysburg by the name of Nicodemus, was defined in a way that essentially it's a dimensionless parameter, and there are various different methods for defining how much light is reflected from the surface, as shown, and I also give the reference to the review paper that actually described how this was done for optical remote sensing. The fundamental method, which is shown in the top left here, is the bidirectional reflectance, which allows you making the assumption that we just have one illumination in the sky, i.e. the sun, which is a point source, and we only measure its reflection. Moving swiftly on to albedo, we have two different definitions, one of which essentially assumes that the sky itself, either if it's a blue sky or if it's a hazy white sky, or if it's a totally white sky from cloud cover, we just make the assumption that there's a single source of illumination, i.e. again, infinitesimally small sun, and we're making the measurements over the entire 2 pi hemisphere. The alternative, which is much more realistic, is if we have a blue sky plus haze plus breaks in the cloud as well, is a bihemispherical reflectance. And this shows that we're making the assumption that all the illumination is coming from all different directions, which in some cases can also include backscattered light off the back of clouds, and also forward scattered light from aerosols and dust in the atmosphere. And a simplification is made, which we made on the MODIS instrument, where we call the direct hemispherical reflectance the black sky, because obviously there's only one thing in the sky, which is the illumination of the sun. And the other one is the case where you have a blanket of cloud, which we call a white sky. Now, we've had a number of sensors which are primarily polar orbiting satellites since the early 1980s. In fact, there were polar orbiting satellites in the 1960s, and I recently started investigating some data from the Defense Meteorological Satellite Program from 1972. So it does stretch back a little bit further, but primarily the US National Oceanographic Atmospheric Administration launched a series of the so-called NOAA satellites, which started making systematic measurements from the middle of 1981. That's fairly low resolution of 4.4 kilometers, but you can see this long time series stretching from the early 1980s, and in fact it's still continuing through to the present day. And so this is a source of information about what's happened to albedo in the past. And since 2008, the European Space Agency, through the European Meteorological Satellite Organization, EUMETSAT, has had its own series of satellite, which does include the US AVHRR advanced, very high resolution radiometer system, which, as I say, we have this very long-term record. Then from the late 1980s, we had measurements from a combined French and European Commission system called Végétation 1, Végétation 2. And then that's been taken over by a combined Belgium ISES system, European Space Agency system called PROBA-B. And NASA has contributed multiple instruments, but the primary ones are the multi-angular imaging spectroradiometer called Meyer, or the moderate resolution imaging spectrometer, or MODIS. And it's responsible for developing the MODIS bidirectional reflectance albedo joint with my colleague at Boston University. During the early noughties, there was also 2 European instruments, and since 2012 there's been a NOAA polar platform, and since 2015 a European one. So this shows an example of an albedo product produced over the entire shortwave. We make albedo measurements spectrally, and we also make measurements which are over just the visible part of the spectrum and over the near infrared. So here's an example of one taken just over the entire shortwave, and you can see the expected distribution, which in addition, of course, to the obvious deserts that we can also see the impact of snow, given the fact that this is 2006. And such data sets have been produced at 1 kilometer resolution, half a degree, or 1/20th of a degree, that should say, and half a degree, for every 8 days from the time period from 1998 until 2011. Now, one can also use geostationary satellites to provide similar resolutions of around 5 kilometer. And this shows the bidirectional reflectance factor. And here we can see the kinds of retrievals that we get, in fact, integrated over a 10-day time period. And as you can see, very cloudy regions like tropical forested region of Brazil and part of Argentina has persistent cloud cover during this particular time period in the middle of Southern Hemisphere summer. But in other areas, one can in fact retrieve a combination of the two. So by taking the AVHRR top of the canopy, because I'm not talking about how we actually correct the measurements we make from space to the measurements that we get on the ground by doing atmospheric correction, we get bidirectional reflectance and also temperature. And from the geostationary satellites, we also get bidirectional reflectance factors. And we need to remove the cloud and the snow, or identify where those regions are. And we need to transform the spectral measurements that are made from the satellites into broadband measurements to produce a broadband directional reflectance, which we then use a model which was developed in meteorology called optimal estimation, and taking a climatology from the US MODIS instrument, because that has many issues and many gaps. We use that as a background field where we've created a 16-year climatology to invert and to upscale using energy conservation to get our final data set. So this is the MODIS data, which is available in 7 spectral bands, including 3 in the visible, and going all the way out into the shortwave infrared that we use as a background climatology when we have cloud cover. Now, all of this data takes a huge amount of processing and a huge amount of storage space. So using about 3/4 of a petabyte and 400 cores, the broadband product itself over these 35 years, around 10.5 terabytes, the spectral one about 11, and one that I'm not going to talk about solely for sea ice is around 30. So the final product is daily, monthly at 1/20th of a degree, around 5 kilometer resolution. from 1982 until 2016. Now we can compare our satellites, because one of the problems is how do we know how accurate the retrievals are from a satellite, because obviously it's over a very large area. Well, one of the ways that we can do this assessment is to compare different products together. And this shows an example of comparing the Glob Albedo product on the x-axis with the QA for ECV. So this product here is derived from Bifacial and Meyer with MODIS as an input, and this product here is derived from AVHRR with geostationary data using MODIS also as a background field. And you can see these agree very well with each other. I'll talk a little bit about the accuracy right at the end. But the problem that we have is, how do we relate measurements that we take on the surface, say with an instrument which measures across the entire hemisphere in multiple spectral bands. And the way that we've been doing this is to link it via aircraft measurements. This shows a NASA aircraft which has on board the cloud absorption radiometer. This takes measurements at various different heights above a location that we might have ground-based instrumentation. And this shows you what you get if you look at the bidirectional reflectance hemisphere and what you get from a satellite. And that allows you to connect together measurements made on the ground with measurements with 30-meter footprints, 500-meter footprints, and 275-meter footprints. Now, more recently, towers, which range up to a height of 70 meters, have been employed, and we're leveraging off the back of a very large program to measure carbon dioxide fluxes called FluxNet, the European part of that called Euroflux, the US part called US Flux, the Australian Ausflux, and Asian Flux. So, and included in the instrumentation payload, which I'll show in a moment, you have the same kind of albedometers that have just been shown by Kees. Now, this shows the retrieval that was produced, with the green being in the visible, the near infrared being in the red one here, and the entire shortwave being in the blue area here. Now, we can take this is an example of a base surface radiation network, which is a global network set up by the World Climate Research Programme. And here you can see one of the problems that you have when you try and leverage off other systems, which is the location of this particular tower is at the intersection of a forested area and a bare soil area with some agricultural fields nearby. And one of the things is with ephemeral snow, which is these black marks here, albedo being measured on the left, and time from 1998 until 2011 on the y-axis. And all of the satellite data does cluster together, but frequently the satellites do not pick up this effect and impact of ephemeral snow, which obviously, if you had solar panels located in an area with snow, you'd have good response because of the bifacial sensors that were PV cells that we just heard about, but you wouldn't be able to pick these up from the actual satellite data itself. So here shows a typical tower. This one's in a place called Tumbarumba in New South Wales in Australia. It's at a height of 70 meters. And there's a nice little ladder that you climb up without any safety cage. And when you reach the top, this is the albedometer measuring the downward irradiance, and also this is one measuring the upward radiance. So this has a very large projected field of view. So what we've been doing is taking these surface albedo measurements taken from towers and screening them into skies that contain aerosols and clouds, and skies that essentially are completely cloud covered. We do that by looking at the ratio of diffuse incoming radiation to total radiation. And we can therefore screen the tower measurements to give us the white sky type of albedo. And we can screen them on the basis of this diffuse to total ratio. And if we want to look at those days where we have blue skies, which we call direct hemispherical reflectance or black sky albedo, again, we can filter these kinds of measurements. Now, one of the keys is how do we connect the projected field of view from the tower, which could be up to 500 meters across, up to the satellite data, which may be as much as 5 kilometers across, as I've just shown. We've been developing a method for doing this using the European Space Agency Sentinel-2 dataset, which is available at 10 meters, operating in the visible. And by locating what are the most common ground types in terms of the bidirectional reflectance that we have from MODIS data, and connecting those to what we have from the bidirectional reflectance factor from the Sentinel-2, we can produce now albedo maps right down to 10-meter resolution. So this means that if you want to actually survey a particular area, this is one means whereby you can take tower measurements and cascade up to look over an entire region if, for example, you wanted to select another potential place to put solar panels. Now, when you take that upscaled albedo that takes the tower albedometer to calibrate the bidirectional reflectance in order to upscale it to the satellite resolution, you can see that you can get very, very good agreement. So in summary, long time series satellite derived broadband and spectral albedo products are available. These include standard products such as the MODIS and Meyer products from the US, from the NASA Distributed Active Archive Centers, but also these newer products which we've generated by fusing US and European polar orbiting and geostationary platform data. All of those products are available through the UK Climate and Environmental Data Archive, and in future will be available through the European Union's Copernicus Climate Data Store, with quality assessment defined through an EU program called European Quality Control. Currently, the accuracies that can be obtained are on the order of 5% absolute with 2% relative. And the system of taking the tower data and upscaling it to the satellite, which can also eventually be used for getting high resolution satellite derived albedo maps around the towers themselves, is now operational, and it's run by a French company called Acri. Now, looking longer term, of course, one of the things that's of interest isn't just the shortwave, which is from 0.25 up to 4.5 microns, but is actually focusing on those regions where the photovoltaics will actually have the highest sensitivity. And in order to do that, you require spectral albedo. And so we're developing a tower-based hyperspectral bidirectional reflectance system to achieve the same kind of albedos that we can for spectral BRDF and albedo, not just for calibrating and validating satellites, but also obviously for looking at the variation over time of the spectral characterization of the albedo of the surface. Thank you very much.
Thank you, Jan-Peter, for the very informative presentation. We've reached the point where we can now address questions from the audience, and I've got a collection here, and hopefully we'll have time to go through them all. If not, please follow up afterwards, as we mentioned earlier, by contacting ISES or the presenter. Let's start with the easy one. I think this goes to Richard. By isotropic, do you mean Lambertian reflection?
Correctly. I mean Lambertian reflection.
Very good. Had to make that official. Richard, also more specifically a detail here. What are the SE and SA parameters in your slide 6? One of the audience members didn't catch that.
Just a moment, I have to scroll back. Slide number 6, or which one?
Slide number 6, and you have parameters SE and SA. Elevation,
sun elevation and sun azimuth.
Azimuth. I hope that addresses the questioners. Thank you. One more for Richard. What is the default value for albedo used for general PV calculations?
Depending on where we apply it, in the order of 15%.
Okay. And let's see. This one's to Ravi or Richard. I'll let you do a toss-up. Is the cost of implementing a bifacial PV module economically justified in the high irradiance sandy desert areas?
Richard, you'd prefer, or you want me to?
Yes, I could talk on that as we're performing such measurements. So there are various ways, as Kees pointed out. There are high quality measurements where you use an additional pyranometer. So if you opt for class A, you have relatively high costs, as you can imagine. So it largely depends on what is the size of the PV plant to be planned. So if you're going for a 50 megawatt plant, I think, and bifacial, I can justify that. What we can think of is, instead of, as our experience is, albedo is very heterogeneous across such a field. I would rather, instead of installing a permanent measurement at one point, to rather replace that with an albedo survey and combine this with the satellite derived data to get the temporal aspect.
Okay. Let's see. Quite a few questions here. There was a comment about spectral dimension, and I think Jan Peters alluded to the fact that spectral albedo is coming. Just be patient. Is there a standard temperature for derating or simple model that uses albedo? Would anyone please answer about the derate effects of possible increased temperatures due to albedo? Okay. We'll take that as a research topic. Let's see. There are several comments and questions about what is a good coating for ground surface that can improve the albedo effect. Rooftop. Is there a developing best practice for increasing the surface albedo using artificial means? Anyone?
This is Richard. I mean, in general, for smaller PV plants, I can imagine, especially if you do rooftop, of course, instead of using dark tar, whatever, to have a white surface. And I think there are plenty of opportunities out there to really increase, and this will boost your yields, certainly.
Okay.
I agree with Richard on the rooftop projects where you have a reflective surface or the white surface. If you can build it up, then it will it will have a very high impact on the performance of the bifacial modules. I think in that case, making it more artificial for the rooftop is possible and doable, instead of a very large 50 megawatt project where you need to do in a large way, which is difficult to achieve.
Thank you.
I'd also like to just make a comment, which is that white rooftop buildings are ideal for cooling the building in hot climates.
That's a very good point. I
So you
believe
get
that
double dipping.
that's right. 2-for-1 benefits.
Right.
Oh, let's see. Here's one for Kees. what is the best way of cleaning pyranometers? What sort of errors are we talking about with regards to infrequent cleaning?
Yeah, Kees here. Cleaning, difficult subject. IEC gives a very simple recommendation, irrespective of whatever climate, so that makes it easy. It's once per week. However, yeah, to be honest, I don't know of many people who actually do that. And what we are seeing in the field is that one big advantage of a pyranometer facing up is that it has a dome. So domes tend to be a little bit more self-cleaning. But basically the answer should be once per week. Down-facing sensors, obviously in many climates don't get dirty that quickly, but anyway, once per week is the general approach. And I often advise people to also take a look at what schedule people clean their cars. Here in the Netherlands, you have to do it every month, and in some parts of China, every 2 days.
That's a good analogy. I would just offer too that what you clean it with is important. You don't want to leave any residues behind, so it's not unusual to use alcohol or some other than a traditional window cleaner. Kees, you spoke about this, but I think there was a few comments about, could you just recap, for PV applications, which do you recommend for albedo measurements? Photodiodes or I think the assumption is thermal pyranometers. And I think the words reference cells could be thrown in that question as well. Could you capture the essence of that issue again, please?
Yeah. The one big advantage of a PV reference cell could be spectral, because it catches the sun just like the PV panel does. So ideally a reference cell would really be a reference cell. However, if you go into detail, and I can talk about it for hours, I don't have that time, but if you talk about temperature response, directional response, calibration, uncertainties, then my impression is that the quality control possible for pyranometers, plus the fact that you can use one instrument for everything, yeah, for the practical people, that often is more important. For the scientific people, or for example, in pre-construction resource assessment, you might have more time and more data analysis, and those practical aspects probably count for less. I'm sorry that I don't have a good answer. There are several schools of thought, and maybe you should not ask me as a pyranometer manufacturer, to be honest.
Well, you were a convenient target, and I trust you for being unbiased. But I would concur with that for what that's worth. We had a comment. Changing the subject a bit here. We had a comment that 30 to 40%. Oh, by the way, this probably should go to Robbie. The comment was 30 to 40% bifacial gains are only possible for single module or very small and isolated systems. With higher GCRs, bifacial gains will be much lower. I think this question begs the issue of scale. Robbie, could you enlighten us about the bifacial gains for larger systems, or address this issue?
Yeah, hi Tom. I just mentioned a study by Trina Solar where they combined the trackers and they had a white banded surface. They could achieve close to 33% bifacial gain. So it's something which is sometimes not ideal, but now I think I just heard today US Department of Energy has awarded a contract to DNV to do a study on the increase of output. I think we look at this study is going to happen in Davis in the US, where several suppliers are going to supply their modules, and also there will be a simulation in the PVC software. I think that can give more insight into the question asked about the higher gain. I think it is too premature at this point of time. The study limited by various manufacturers, and the data are presented. There are various factors contributing to the energy gain. So I think I would suggest that we'll wait for the study which is being conducted along with trackers, along with various other module technologies, because we are mostly N-type technology being used, but some of them are using P-type technologies. And I mentioned about a couple of other factors. So we need to look at, for the large deployment gain, more studies before we can conclude on the exactness of the gain. We can think about it using bifacial modules.
Very good, thank you. Here's an easy one, again, back to Kees. Question was, have the ISO standards been revised recently? This is ISO, not IEC.
Yeah, yes. ISO 9060, the old standard is from 1990. There is a new version of the same standard approved just a couple of weeks ago, but it didn't appear in print yet. This will happen in the month of December, presumably.
Great, so we should keep an eye on our website. This is a question to Jan Peter. I'm going to read it directly. What is the percentage uncertainty to albedo measurements from satellite? Also, what is the difference observed in readings between satellite and actual double pyranometer measurements for albedo? I believe you had some slides, you presented on this, but can you capture a sort of a rule of thumb? Is that possible on this percentage uncertainty of albedo measurements from satellite, just to reiterate?
There is a difference between an instantaneous measurement of albedo, which we have restricted satellite sensors which actually provide that. The only one that's operational is the Meyer instrument with 1 kilometer resolution. And we produce from Meyer and from MODIS and from these other products an uncertainty estimate, an uncertainty budget. And that uncertainty is primarily for when we are using an integral of multiple measurements of different angles taken from satellite observations on different days, and typically with MODIS, for example, over 16 days. And therefore, it doesn't make any sense to compare with an instantaneous measurement. It only makes sense to compare with the measurements over the same time period. I gave the results that most of those ones that have been assessed over homogeneous targets from tower albedometer measurements are within the budget or predicted error of 5% absolute, and point to point, that's pixel to pixel within a satellite measurement, to 2%. Now, one of the biggest issues that we face with satellite measurements is, are the measurements made in 2000, in the year 2000, on the 20th of November, are they the same as the measurements on 20th of November 2018? And that refers to whether or not we have characterized well enough the actual measurement radiometers on board the satellite over that 18-year time period. And that's been a particularly acute problem with these AVHRR sensors, because they weren't designed to be climate measurement systems. They were designed just for instantaneous meteorological measurements. The good news is that since 2000, when we have all of these polar orbiting satellites, we have very, very accurate calibration, not just pre-flight, but also taken from ground measurements called vicarious calibration, such that we have now measurements accurate to the order of 1%. So that means we can characterize the measurements made in November of 2000, and we can say that the same measurements are made to within 1% of the radiance value in 2018.
Thank you very much. Another question came in. Aggregation. We have the high temporal resolution ground-based albedo data. Richard, can you help us understand if there is a process to aggregate such data into monthly albedos? Is there a best practice for that?
If you refer to satellite derived or ground-based?
Well, the question comes in as ground-based albedo data,
okay.
And how to get it into longer time intervals, such as monthly albedo.
It's simple averaging. So with the ground-based, you have the advantage. It measures also under cloudy skies, so you don't have some bias, because under non-cloudy skies, this is when the satellite works. You might have drier surface, but so for the ground-based, a simple averaging.
Okay, I think the issue might be data quality, which is a topic unto itself. You know, how to handle missing data, interpolation, extrapolation, what have you. But I guess I would personally offer that the systems that are in place, when they're well maintained and well designed, the data quality aspects can still take a lot of time. But I think we've seen a vast improvement of late with the systems that are in place. So as you say, Richard, this really boils down to make sure the data are what you want to average, and then just do the simple math. I hope that answers the audience question. I'm sorry, go ahead.
Just an additional recommendation, to get more accurate values, I recommend to filter out usually like sun height below, just filter if sun is above 10 degrees height.
Very good. Yes, those sunrise sunset times are tricky. Let's see, here's a rather simple one. We have we're less than a minute. Let's conclude with this question. Please define spectral albedo versus narrow band albedo. Any takers on that? I'm not sure how to direct that question.
Yeah, I'm happy to answer that. Normally, if you're speaking about satellite or aircraft or even tower-based sensors, spectral refers to multispectral. So we have bandwidths on the order between 10 and 50 nanometers, whereas spectral albedos more typically nowadays refer to hyperspectral, which means that you're making measurements in bands which are below 10 nanometers. Some of these systems now go even less than 1 nanometer. So that's the usual differential that I would propose. Very good. Well, with that, people, I think we'll have to conclude the Q&A session. And I want to thank the audience for joining our webinar today and asking these questions. All very helpful. And thanks to the presenters for sharing their expertise. And it's been my pleasure to moderate. And now I'll turn the controls back to Jenny.
Great. Thank you, everyone. And thanks for the excellent presentations and the excellent question and answers from our audience. I just wanted to quickly conclude by letting everyone know we have a webinar every month, as most of you know, and we have one coming up here on the 12th of December on the IEA Solar Heating Cooling Task 57, Solar Standards and Certification. And in early 2019, we'll have our second webinar series on women in solar energy. So I hope you can join us for those. I also wanted to mention that a survey will be launched after this webinar for the participants. So we welcome you to please complete the survey to help us improve and get your feedback on what we're doing well. And yeah, and that's it. So I just wanted to thank everyone again. Thank you, Tom, for moderating so well, and all of our speakers for your excellent presentations and sharing your expertise with us today. And yeah, that's it from my side. So thanks, everyone, and we'll hope to see you again on another webinar soon.
Thank you, Jenny.
Okay, thanks, everyone.
Yes, thank you. Thank you. That was fun.
Thank you, Tom. Thank you all.
You're most welcome.
Thanks to all of you. Bye-bye.
Bye.
Thank you. Bye-bye.
Bye-bye.
Bye.
Thanks. Bye.